Good morning. Here are some notes on section 3.5 exponential and logarithmic models. I'm not going to worry about these terms. The ones I want you to really focus on for this unit are the exponential growth model, and we use this to find out how many we use something similar to this to figure out how many dominoes it would take to knock over a skyscraper. And then the exponential decay model is just, it's the same, we just have a b value that is, or we're just going to have this negative in here. I will go ahead and write out the logarithmic growth model just in case it comes up. That's a over 1 plus b e to the negative rx. And then we've got a couple of different logarithmic models. A plus b log base 10 of x. So you can just write those down, and what I really want to do is practice using the growth model for a population growth problem and then a carbon dating half-life type problem. So this will be growth, this will be decay. In example 1, suppose a population is growing to the model p equals 800 times e to the 0.05 t, where t is given in years. What is the initial size of the population? So we saw this formula when we did our domino skyscraper, and this initial value right here is 800. That's when t is 0, so all this stuff, e to the 0 equals 1, and 1 times whatever this coefficient is will give you your initial value. So when it says how long will it take this population to double, you can simply figure out what the population would be doubled. If it starts at 800, doubling would be 1600. And then there's the rest of the formula. But always when you're doing a doubling problem, your first step is going to be a division, and then you end up with a 2 over here. So that 2 signifies the doubling, and then e to the 0.05 t. Now, if we want to use our loop trick, and I'm going to just put my 2 over here so that my loop can be in the same counterclockwise direction every time, and I do the natural log base e of 2 equals 0.05 t, and then the natural log base e of 2 would be 0.693, and then to get t by itself, divide by 0.05 on both sides, and we get 13.86. And then we want to check and make sure, does that make sense in the context of our problem? Well, is that a reasonable number of years for a population to double? Yes, it's a normal number of years. So that shows how, even though these are called growth exponentials, this is really just a continuation of what we've been learning all along in this chapter. So for example 2, it says to estimate the age of dead organic matter. So let's see here. That is carbon dating. Let's see. They call it carbon dating model. I don't know what the name of it is. Maybe like half-life. So the ratio R of carbon 14 to carbon 12 at any given time. And carbon 14 has a half-life of 5,700 years. So the ratio of carbon 14 to carbon 12 is R equals 10 to the negative 16. Find the age of the fossil. So, oh, okay, here I was supposed to write out the formula. You're going to kind of need that to solve this problem. So it's 1 over 10 to the 12th times e to the negative t over 8,223. And so here we're given an r value of 10 to the negative 16th. So I'm going to plug that in where r is in my formula. And actually, let me find a better place to show some work here. Well, let me just get a blank page. Okay, so let me rewrite my formula nice and neat. R equals 1 over 10 to the 12th e negative t over 8,223. And then I'm going to substitute the r value that I was given in this problem. So 10 to the negative 16th equals 1 over 10 to the 12th times e to the negative t over 8,223. So you can see this is just a substitution problem, and then with our e we're going to end up using a natural log at some point. So let me go ahead and multiply this out times 10 to the 12th. So here we're going to use our exponent rules. 10 to the 12th times 10 to the negative 16th. We add our exponents. So 10 to the negative 4th equals e to the negative t over 8,223. And now we've got an e and a variable up in the exponent, and so that's a signal that we want to use or change it into a logarithmic form. So I am going to go ahead, I just wrote my answer over here so that I can use my loop. And since I'm using e, I'm going to take the natural log base e of 10 to the negative 4th equals negative t over 8,223. Multiply by that on both sides. And I'm going to get, let's see, 10 to the negative 4th. And then take the natural log of that times 8,223. I get this big negative number, and then that equals negative t. So my final answer, 75736.6. So that's going to equal positive t. So that fossil is 75,736.6 years old. So that is an example of one exponential growth problem and one exponential decay problem.